Connecting to cloud server? Oh, did I? Hello? Are we all here? Yeah.
Yeah,
Okay. That's good. For some reason, the cloud service interrupted. I think they did something different with Zoom. Did you need to like load a new version of Zoom today? I did. And they warned me that
I didn't.
something was going to change. And all right, whatever. Roll with it. Our lizard overlords are in control. Not to worry. Okay, so we have these sliders, right? Oh, so look what happens there. Whoa. So depending on this value of A, we are getting a solution here, right? And that is, well, let's zoom in a little bit on the x-axis as well, right? We're just interested in this region between -1 and 1, really, right? Okay. Yeah, that's where we're focusing, right? Um, yeah. So depending upon this value of A, you know, there's a little sort of critical point there, right, where it flips from one behavior to another behavior. And then, wait, oh, but A is negative there, right? So if A is negative, then we don't get any solutions, right? But if A is positive, and where's that? That happens right about here, right? That is that sort of critical point, huh? So maybe uh, maybe I'll try uh, saying object properties, and I just want to go from 0 to 5. Okay, so then we don't, yeah, so we do, you see the solution is over here, right? And are we getting a solution here? Well, no, A is 0, you don't get a solution, right? So, but if A, as long as A is slightly positive, we get a solution. And here, there it is there, right? Near this vertical asymptote at 0.6 something. How about this B? Yeah, B is negative, then we have troubles, right? So let's go ahead and edit that as well. Um, we want B to be positive, right? So as long as B is positive, if B is 0, we got some weirdness. But if B is positive, then we have a solution right here, right? So, I think this is an excuse for you to do some algebra, right? What algebra is that? And notice that it looks like the solution is probably over here, but um, yeah, if it's 0, then you don't get, oh, look at how close to 1 it is there, right? Wow. So this is a genuinely difficult problem. So we're not going to solve it here and now. We just wanted to get a feeling for what the heck is going on with this thing. And do we have a plan for dealing with it? I think we probably want to combine these two. Maybe you want to see what's going on with F and what's going on with G at the same time, right? And I think we should go on to 2.6. But yeah, this looks like a lot of fun here. So I think I can actually save this so we don't have to worry about rebuilding it, right? So I'm going to save this as, you can't see my dialog window for that. I'll just give it a name. Stuart, uh, Stuart, um, 2.6 dash, what was it, 72 or something, 73. Okay, and I'm going to close this, and I'm going to go over here and say, yeah, chapter 2, get me out of there. Sorry, I need to show you the display capture, which is here, and 2.6, limits at infinity, horizontal asymptotes. Yeah, for rational functions, um, if the degree of the numerator is equal to the degree of the denominator, then the ratio of leading coefficients. I think let's just get right into the exercises here. I know it's wrong to skip the exposition, but we don't have a lot of time, and I'll try to get to the exposition as in response to the question, right? So what happens as x increases without bound here, right? That's our question. And I'm just wondering, can I make this larger? I tried zooming in before. Didn't seem to. Okay, I guess that's a little bit better. Explain in your own words what the following mean. Well, okay, so let me see. Can I explain this in words? Let me try using my, uh-huh. Okay, that's blue, and this is the eraser. Okay, so can I see where, yeah, I can, okay. So this is going to say, we can make, I'm sorry, I cannot write. We can make f of x as close to 5 as we like by taking by choosing x large enough. Does that say it? Well, maybe not, right? So let me try again. And I really don't know if I'm going to be able to learn how to write with this thing. How are we doing time-wise? Yeah, I got 10 minutes. So the more formal way of saying this is given at any epsilon greater than 0, we can find n such that, find n such that x greater than n implies that the difference between f of x and 5, so the distance from f of x to 5 is less than epsilon. Well, that's pretty tortured writing, but is the idea clear enough? And down here, the only difference is that, you know, I'm going to say for all epsilon greater than 0, we can find n so that x less than n implies that the distance between f of x, and how do we write this? Absolute value of f of x minus 3, so that the distance from f of x to 3 is less than epsilon. Okay. Yeah, and that was actually kind of perfect for establishing the exposition that leads to that problem, right? So we didn't read the text this time. We just went straight to the exercises. And so far, so good, huh? What else we got here? 2, can the graph of y equals f of x intersect a vertical asymptote? Can it intersect a horizontal asymptote? Okay, so for a vertical asymptote, we've got sort of the horizontal line problem, right? So if we got a vertical asymptote like this, couldn't we make the, sort of arbitrarily define the function to have a value on the asymptote? in which case, yes. And certainly a horizontal asymptote, right? And again, I don't know if this is going to work, right? So you could have a function that does something like this, right? Approaches the horizontal asymptote asymptotically, but yeah, it does intersect over here, right? And so I would say yes in both cases, but you know, it requires some splaining. Okay, so for the function whose graph is given, state the following. Oh, where's the graph? Okay, here, huh? So maybe I need to zoom out a little here. Okay. Can we see what's going on? So what happens as x goes to infinity? Well, we can't really say, can we, right? Oh, and if I set my stylus on the surface, it kind of freaks it out. Can we say what happens as x goes to infinity? Are you supposed to assume, oh, it's approaching -2? I would say that's a stretch. X approaches -infinity. Well, maybe it's approaching 2, maybe not, right? Because we just don't see that, right? So I think it's a bit of a stretch to extrapolate from a graph what happens at infinity, because you just can't show it, right? What happens as x goes to 1? Well, clearly the intention is that limit is infinity, right? As x goes to 3, -infinity. I mean, that's the implication of what's shown, right? The equations of the asymptotes are y equals -2, y equals +2, x equals 1, and x equals 3. Okay. For a function whose graphs state the following. Okay, let's move on. Guess the value of the limit. Okay, so 2.6, I haven't assigned you exercises yet, have I? Okay, I will do that as soon as we're done reading some of these problems. Guess the value of the limit. Oh, okay, this is kind of interesting. X squared over 2 to the x as x goes to infinity. Well, you know, this is the old race between a polynomial and an exponential. In the long run, the exponential wins, right? So 2 to the x is going to grow much, much faster than x squared, even though they're both going to infinity. And so this limit is going to be 0. Is that? I guess it's not obvious, is it? Is it obvious? I don't see anybody chiming in the chat. Yeah, I would say that's you know, there's tools that we don't have yet which we could use, but 2 to the x is equal to e to the can I write this here? So this is the limit. We just need to give this up, right? As x goes to infinity of x squared. I mean, we don't really have the tools we need to, so you're just going to have to, you could say this, right? That it's e to the natural log 2 times x, right? Because e to the natural log 2 is 2, and 2 to the x, right? Then, so the idea being there that, yeah, that doesn't really help us here, right? Okay, they basically, they just want you to get numerical evidence and then use a graph to support your guess. So the best you can do here with the tools we currently have is guess, which is kind of unsatisfying, right? But you know, you can get some intuition as to what's going on. So what happens here? Well, here the degree of the numerator equals the degree of the denominator. So let's just go to pencil and paper, shall we? I mean, it's just ridiculous trying to write on this thing. And for that, we need to be over here. And I'm going to move this up and say, so this is 2.6, number 13. And this is the limit as x goes to infinity of 2x squared minus 7 over 5x squared plus x minus 3. And we can divide the top and the bottom by x squared. That's one way to do this, right? And so you're going to get 2 minus 7 over x squared in the numerator, and you're going to get 5 plus 1 over x minus 3 over x squared, right? Is it clear what's happening there as x gets large? All these terms with x in the denominator are going to go to 0, and the ratio is going to go to 2/5. And this is something you would have learned in pre-calculus already, right? That for a rational function, if the degree of the numerator equals the degree of the denominator, then the horizontal asymptote is the ratio of leading coefficients, which is 2/5 here, right? So this is just 2/5. Okay, so if we go back to our exercises here, are there any more interesting ones here? Well, here the degree of the numerator, and I'm looking at number 22. Degree of the numerator is 4. The degree of the denominator is also 4, right? Because you're going to be squaring that. And so the leading coefficients are then 4 over 1. So that's going to go to 4. How about with if you don't have a rational, right? But the numerator here behaves like x as x gets large. And, let's talk about that one. So display capture. Okay, we're just about done here, but maybe let's get this number 23 out of the way. And then I will immediately load up some WebAssign problems. We should also look at these problems. These are perfectly good problems, right? So this is the limit as x goes to infinity of square root of x plus 3x squared all over 4x minus 1. So I'm going to say I can factor in x. Actually, I'm going to factor the positive square root of x squared out of that, which actually technically is the absolute value of x. And then what's left? Well, you're going to have 1 over x plus 3 under there, right? And this is 4x minus 1. So now as x goes to infinity, the absolute value of x is just x, right? So you can see that, yeah, this thing under the radical is going to go to square root of 3 because 1 over x goes to 0, right? As x gets large, the reciprocal goes to 0. And so that's going to be, we're out of time. So this is just going to be square root of 3 over 4. All right, I'm going to set up some WebAssign for 2.6. Any questions before we quit? Oh, I see. I have a question. When did you upload another section of 2.4? Because when I was working on my homework throughout the day yesterday, I saw only saw 2.4, the definition of limits, and not 2 sections of 2.4. Is there another section of 2.4? Let me look at that. I see only one. Yeah, there's only one. You shouldn't see more than one. Sometimes I do make the mistake of like, oh, I haven't done that yet. I do it again because I've already done it and forgotten. But I don't think that happened here. Okay. All right. Well, I'll be in my office, 12:10 to 1:10. And sometimes I'm a little late to the 12:10 because, like we're doing now, I tend to go over a little. So let me avoid doing that, and we'll call this to a close. I'll bid you a pleasant day, and maybe I'll see you later this afternoon. Ciao for now.